Hello everyone. In this video, we are going to cover D5, that is further cosmology from astrophysics. And first topic, we start with a cosmological principle. In a cosmological principle, you will find it is composed of two important principles. And the first principle is about homogeneity. Now, in this, if we cut a universe in a pieces of cubes which are about 300 megaparsec a size, you will find that inside that cube, whatever the galaxies are, you will see that the cubes are similar to each other. It means the universe is homogeneous. It is not that in a particular part of a region there is any specific thing happening or more galaxies as compared to any other part of the universe. So universe is homogeneous. So it implies that the universe does not have an edge, because if universe had an edge, then the part near the edge would have looked little bit different as compared to the part that we are looking at now. Now, this is something that we always need to assume in cosmology, these two principles. Like the universe is also uniform. It means that the density of the universe throughout the space, anywhere you go, will be mostly same. The second principle is about isotropy of the principle. Now, according to isotropy, if you look in a particular direction, you will find the same number of galaxies, or all the laws of physics in any particular direction are working in a very similar way. So isotropy is related to direction. So in any direction, if you point your telescope, you will find similar amount of matter. Okay, and that's how the universe is spread out. So according to isotropy, the universe has no center, because if it did, then from the center the things would have looked little bit different as compared to away from the center. So these two principles are always kept in mind when we are studying cosmology. Now, we learned about cosmic microwave background radiation in D3. So in that particular cosmic, what is cosmic microwave background radiation? A cosmic microwave background radiation is a radiation, leftover radiation from a Big Bang, and that radiation was observed in a uniformly in all the direction that where we point the telescope, and it is in microwave region, and that's why it is called as cosmic microwave background radiation, because we assume that the universe when in its earlier days was very much hot. So that also supports the theory of Big Bang. Now, in that particular cosmic microwave background radiation, we find some anomalies or anisotropies, that the temperature fluctuations, okay, are there. The temperature is not constant single value, the density is not constant. Okay, the variation is temperature are related to variation in density of the universe, density of how the galaxies and the matter is spread out. Now they are assumed that the density perturbation are believed to be the effect of quantum fluctuations. Okay, during the expansion there might be some fluctuation at quantum field or quantum level that would have caused this. And this is very important because this variations serves as a seeds for the formation of structures like stars and galaxies in the universe. It is very important. See, imagine the temperature of the universe is uniform, or the density of the universe is uniform. How does the energy will transfer from one point to another point? Because for temperature to change, there should be some heat or some energy needs to transfer. For movement of particles, there needs to be some areas that need to have different density than others. So if the universe was completely uniform and temperature and density would have been constant, then what we will see that no stars or galaxy would have been formed. So that's a good thing, but important thing, it also aids to the understanding of our universe. Now, this universe can have a different structure We can have a curvature that is called a flat curvature, positive curvature, or a negative curvature. Now it depends. We will go it in deeper when we learn about what is cosmic scale factor and how it depends on the time and what are those curvatures also. But there are different possibilities, there are different theories that indicates, and we see the cosmic background radiation has a data that supports each of these possibilities. So there is still more a question and we are trying to figure it out. Then we will learn about something that is called as rotation curve. Now rotation curves are nothing but a graph of velocity versus the radius. So imagine there is a graph of velocity and distance. Now consider our sun, which is a mass m, and there are planets at different distance orbiting the sun. Then what we will see is that the orbital velocity of the planet will be given as square root of capital G, that is gravitational constant, m by r, where r is the distance from the center. Okay, so it means that a graph, if we plot a graph, the graph will most likely look like a curve like this. So this is it is a distance from the sun in terms of AU, atomic unit, and this is a orbital speed. So this is the curve, and this is something that we call as rotation curve. Now this is not the only possibility. Imagine there are galaxies, or imagine there is a dust cloud. So consider a dust and gas spherical cloud of mass m and radius r. Now inside this there is a small mass, some other small mass is there, which is at distance some r, which is also rotating about the center, but it is inside the spherical gas cloud. If it is inside the spherical gas cloud, the orbital velocity for that can be given as, again we can write this as V gm by r, but here r depends on density, the mass of it times the volume, and since we are considering only the volume of this r part, not the entire volume of the sphere, we will write density times the volume will be 4 by 3 pi r cube. Now if I substitute this mass here, I will get the orbital speed to be root of g rho 4 by 3 pi r cube upon r, and you will get that. So if I take this 4 by 3 g rho pi, the r square will get out of circle and we will get r like this. So if I plot V versus r in this case, I will get a straight line passing through origin. So this is another example of a rotational curve. Now when we calculated the rotational curves of different stars orbiting the center of our galaxies, so if there is a galaxy, if there is a center, and our galaxy are, or all the stars are orbiting the center of our galaxies. So they plotted this data, and you can see that here somewhere around 9 kilopascals the sun is from the center. 9 kilopascal is the distance away from the center, and you will see that the speeds are like this. And what this part that we are seeing, the edge of the galaxy, visible edge of the galaxy, is roughly around 15 kilopascal. So till the visible edge of the galaxies, the data seems to be okay depending on how the mass and how the stars are orbiting the center. But what was interesting for the scientists was this flatness beyond the visible edge of galaxy. Now this flat curve is only possible, and we can model this. This is only possible when a mass of certain quantity is directly proportional to some constant times the radius. Like not radius, like distance from the center. Okay. In this case, only during this case, you will see that if I substitute this in V orbital root gm by r, I will get root of gm. So it will give me a curve V versus r. The graph will be like a flat line, which is root of gm. Now this is what they are saying. And if this is true about this matter, which is giving the flat line beyond the edge of the galaxy, we will see that since r is big, it is about 16 kilopascal, this ion should be also very large. So there is large substantial amount of mass that is away from the center of the away from the center of our galaxy, and this mass was referred to as dark matter, which is not visible. It does not interact with light. Interact with light. Okay, and that's why we wouldn't able to recognize it. But since it is so massive, it is roughly said that in the visible matter in our galaxy, almost 85% is dark matter. Okay, now what is dark matter? You can see the dark matter halo. It is probably this picture is just exaggeration of what the real situation is, but the dark matter is completely non-interactive with the light. That's why you couldn't see it. Now there are few candidates or possibilities. So there are different theories about dark matter, but these are the possibilities that we support. One of the possibilities is machos. Now this is a short form for massive, that is Ma of massive, compact halo objects. Which means basically the black dwarf, the reminiscent of a white dwarf, then a brown dwarf, brown or red dwarf, okay, and some small planets. Now these are the possible machos, or these are the possibilities that there can be used, because all those do not produce their own light, and basically when the further distance away they won't be visible, not producing any other radiation also. So that's the one theory about one possibility about dark matter. The second is WIMPs, that is weakly interacting massive particles. Now, weakly interacting, that's something that we can give an example of a neutrino. A neutrino is so light does not interact with most of the matter, but it is there, it is present, it has been detected. And what usually happens is, like, there could be millions of neutrinos that could be passing through Earth right now, because they are so non-reactive with most of the things. So it is a good candidate, but the mass of the neutrino is so small, it can't constitute for like 85% of the mass of our galaxy, which is predicted for a dark matter mass. So there can be other particles which are Now these are the particles which are black dwarf. They are mostly made up of baryons. So we also call them as baryonic matter because they are mostly consist of neutrons, protons, and uh, electrons. Okay. Now electron is not a baryon, but most of the particles usually those particles you will see that neutrons and proton will be in a large quantities. Now other candidates might be some undiscovered particles. So there is a supersymmetry theory which predicts like there could be some particles which are non-interacting and they have much heavier mass also. So these are the few candidates about the dark matter. Now temperature of cosmic background radiation, according to Wein's law, that lambda is inversely proportional to temperature. And we have learned in D3 the wavelength that we observe upon the wavelength upon emitted is equal to the cosmic scale factor in present upon cosmic scale factor in past. But since wavelength is inversely proportional to temperature, the temperature of cosmic microwave background radiation could be written as something like this. T is temperature of CMBI, cosmic microwave background radiation. So this is where we can use this. So what we predict is when we see the wavelength, okay, the lambda observed is greater than what we have seen lambda naught because it was so. According to that, the temperature would have been much higher in the past. Now it is colder now. So that's why roughly the temperature of cosmic background radiation, the average temperature is roughly around 2.7 Kelvin. Okay, but we assume it to be much more hotter in the past. Then another quantity we have something like called as critical density. So for this derivation, which is important, they might ask this derivation. So imagine there is a spherical cloud. Spherical dust and gas cloud. And imagine there is a small mass or a galaxy which is moving away. Okay. And let's say this is at distance d from the center. Okay. Now, if this mass, this spherical gas mass, will have its own gravity that is attracting it. So if I write total energy of this mass m moving with velocity v away from center, then that will be given as half mv square, that is the kinetic energy, minus gmm by d. Now what we can see is that this v, we are assuming that this v obeys Hubble's law. So this small mass is just like a galaxy which is expanding with the expanding universe, okay, which is moving away from us because of the expansion of the universe. So this galaxy will obey Hubble's law, and according to Hubble's law, V will be equal to h naught into d. Okay, and if the density is constant, that is something that we are assuming, the mass m can be written as density times 4 by 3 pi d cube. Okay, so what we will get if we substitute those, replace V and M, we'll get the total energy to be equal to half m. Instead of v, we will write h naught d the whole square minus g. Instead of m, we will write 4 by 3 pi d cube into m upon t. So if we simplify this and take out half m d square, what we will get is h naught square. Okay, we will get h naught square minus 8 by 3 pi rho g. Okay, so we will get this factor because this d and this d will become square. So these are the things that you will get. That is the total energy of the universe. Okay. Now this equation leads to different possibilities. Okay. It means that if E is equal to 0, it means the expansion will continue and halt at infinity. In that case, we will get a density that is called as critical density. So expansion will halt and contraction will start. The critical density will be given from this equation. Equate this to 0 and you will get 3h naught square upon 8 pi g. Okay, so this is a critical density because if the universe had anything less than critical density, so if ET was less than 0, then in that case you would have got the universe will be, there will be more gravitational potential energy, so the expansion will halt much more quickly and then contract under its own gravity. Okay, so this critical point basically gives us different possibilities, and that's what we are going to learn in this last factor, that is variation of cosmic scale factor. Now, cosmic scale factor is like a grid that we are learning, the grid on which all the galaxies and stars are placed, and this grid is expanding, and most likely the important candidate that we are thinking is responsible is called as dark energy. Okay, now dark energy is the energy that fills up entire space. Sometimes it is also called as vacuum energy. Now this energy not only acts repulsive, but it is kind of stronger than gravity. Okay, that's the reason why we observe an accelerating universe. Okay, now this dark energy is still not clear exactly what, but we know that it constitutes about 68 to 70% of existing energy and matter in the universe. Okay, so there is a huge which is able to stretch or push the galaxies away from each other, and this is the main candidate. Now, Einstein tried to solve this and got a relationship between a cosmic scale factor and time, how the cosmic scale factor will evolve with the time. Okay, and he had no idea exactly about what is dark energy. Okay, and there's someone called Friedman, okay, who introduced these two quantities like density. We call this as density parameters. According to density parameters, there are two kinds of density parameter. One depends on the actual mass of the universe. This is density of actual universe upon the critical density. Now, and then there is one more parameter, that is rho. And this sign, it is a lambda sign, which gives us density of dark matter. And this is upon the critical density. Okay, so these are the two density parameters which we solve when we solve these equations related to scale factor and time. We probably get 4 solutions. Now, out of the 4 solutions, 3 solutions assumes that the dark energy, there is no dark energy, and the dark energy is 0. In that case, we will find the 3 possible situations. Something that we call as first is open model. Now, in the open model, what we are considering is that there is open model, there is closed model, and then there is a critical model. Now, in open model, what we are assuming that the universe has a negative curvature. Like the expansion in this open model, the expansion will never stop. Okay, the blue line here represents the open, and here the density of the universe is less than the critical density. Okay, the density of the universe is less than the critical density in that case. So this rho will be less than 1. In closed model, we are assuming it to have a positive curvature. In this positive curvature, the expansion not only stops, but the gravity overpowers the expansion, and then the contraction leads to like everything converging together. There is something also called as big crunch, the event of big crunch. So all the galaxies, the gravity will dominate, and this is something you will see. So this is only when the matter is more than the critical density, then in that case there will be more gravity. And then the last model is a critical model, where we assume this is equal and the rho m will be equal to 1. In this case, we will explain there is a flat universe and the expansion will halt at infinity. Now, in the fourth solution of the equation, we assume there is a presence of dark energy, and this is something that our data and observations supports. So we have not only predicted but rather proved, because of the data that we have, that there is a presence of dark energy, and that's the reason why the universe will accelerate, and this red curve expansion, the expansion keeps on increasing In that case, all the galaxies will go away eventually, so much that the night sky will be almost empty. Okay, so this is what we will see. Okay, so these are the different models, and this is something that where we complete the astrophysics D5 also. Thank you so much.